So thank you very much for inviting me again. It's all the time. I think I'm invited since last 2008 from the beginning. I think that's good. Okay. And thanks to Professor Ali Ganjar and all the organizing committee to invite me in this nice conference. But only the pity thing that I can't go there. That's the only problem. All right, so today I will talk about the strategies to improve the in-field performance of near isotropic. This is important keyword, near isotropic MgB2 conductor for magnet application. So this work actually it was done a long time ago, but we found some important insight, important understanding, investigation. So we recently actually published this work together with, I think Andre Moroski also here, Daniel Carmine Senatore, my postdoc supervisor, Professor Plukiger, my PhD supervisor, Professor Dow, and my industry partners, Avesium and Hypertech. All right, I'm Hossain from Australia, University of Queensland, and I'm working in the School of Mining Engineering and Faculty of Engineering at Australian Institute for Bioengineering and Nanotechnology I'm affiliated with. All right, so the next slide. The next slide is very general information. I think you all know that many superconducting materials around discovered, more than 10,000 if you look at the periodic table. And if you filter the in terms of the properties, that's actually very in terms of the properties for application, that's actually is quite less number. Like TC for more than 4.2K and BC2 more than 10 Tesla is around 100 only. But if really you need the superconductor for real applications, you need the JC at least 1000 ampere per minute square, which is only few, 10, even less than the 10. And these are all the materials so far discovered. This low temperature superconductor, medium temperature MgB2. I will talk about the MgB2, and also you see all these complicated high temperature superconductor as well. And recently the room temperature superconductor discovered, but you know that the compromised with temperature, but it's not compromised with the pressure. The pressure is around 2667 gigapascal. It's required even at room temperature, but it is not there, I think. So anyway, so we will talk about MgB2 today because there are many so far, because okay, MgB2, I was waiting for June's talk, but it was cancelled. So the MgB2 discovered around 20 years ago, but still we are not in that position that we have to, because this is only not the how can I say, it's not even what we expected. It's not implemented and applied in a device fabrication. So niobium, titanium is still the workhorse in a commercial market. But the problem is we have the motivation for MgB2 in liquid helium free, because liquid helium free application, because of, you know, the liquid helium is getting expensive every day by day. And the niobium titanium, you see that another problem is the TC 9.2K. Its cryogen free operation is really difficult because the TC margin is really low. Is 9.2K and 4.2, so this is very risky for the application. So we don't want to talk at this moment with low temperature superconductor. I mean, if you look at the high temperature superconductor, it's really complicated structure you see in the bottom here, and the problem is the manufacturing. The manufacturing is very complicated. It's very hard to get the long length of conductor, because if you can't make a long length, you have to make a joint, and those joint, if you have a 1 kilometer and if you have 100 joint, is just to reduce the mechanical reliability. So, and it is also, you see all the rare earth material is very expensive. So we can also cancelled those. So let's talk about magnesium diboride, and it is, the TC is 39K. That 39K give the room of opportunity to use the liquid helium-free operation. And it's a very simple structure. In the last few talk, you can already know about that. That's very simple structure, easy to manufacture, definitely. Fabrication cost, low weight is very, cost is low. ITC, helium-free cooling is possible and highly anticipated to replace the niobium-based alloys in magnet system. We are expecting actually far long ago, but still it's not that mature what we are expected. Okay. So these are the fabrication process. As we all know, because we are here, everyone in MGB2 research area. So you have the in situ. This is the ex situ. In situ, you can have all the flexibility to improve, but ex situ, as you see, it is already commercial reacted MGB2. And then these two, you have you can do the ball milling, then put into the tube, and then the heat treatment and draw and make a draw, and then you put the heat treatment. And another one is CTFF, continuous tube filling and forming, which I'm working with Hypertech at this moment. So Hypertech, my industry partner from my PhD study. So they are actually, they have the patented technology. This is kind of in situ, but it is just tube filling and forming. You can see in many publications, you can see the process that it's just going, the tube fill and then form. And another one, we have now the second generation of MGB2, which is internal magnesium diffusion, where the magnesium rod is there around the boron powder, and then you draw you can see the after the heat treatment, actually the hole inside, and this is another problem I will explain maybe a little later. So let's talk about how actually this MGB2 form in a wire. So these are the magnesium and boron. So when you draw the wire, the magnesium is ductile, is get elongated, and it's just distributed with boron powder. When it is heat treated, then it gets the diffuse, the magnesium, and there's a melt, and then it's created actually a few different type of voids, which is elongated. Some voids are micro voids, and it makes the conductor. Sometimes you need to reduce this void. So this is the last few years, actually, these voids, how to reduction, that's actually big research area. So it's going on. In last few talks, we already found that these voids are not good for improve the connectivity. And if you look at this is, as in first Andre's lecture, actually he said that lamellar structure, this lamellar structure also important for improving the JC. So this is the combination of micro and elongated voids also there. All right, so as you already know that how to improve the in-field performance of MGB2 wire is very, very important. We need to not only improve the high field, we have to improve the low field as well. So if you look at this paper, Ted Collins published in 2008, that MGB2 wire can be improved, the performance can be improved by intrinsically and extrinsically. By intrinsically, you can use the different doping, improve the DC2, and this is only you can improve the high field. But the low field, you need to compromise if you look at if you put different doping. But the low field, you need to reduce the porosity to improve the connectivity between the grains, and this is extrinsic. So combination of these two techniques, you can have the in-field performance. So the doping, actually, if you look at the intrinsically, if I can say, different doping has been many dopings already tried, and so far the carbon doping is established doping for improving the high field, definitely. And if you look at this model, Professor Dow published in 2018 in PRL, where the doping, he classified those doping where the substitution and the formation of MGB2 should be at the same time. So this is the dual reaction model. So this model actually gives us the direction how to improve further by doping. And for the low field enhancement, we have to consider these things: reduction of porosity, improving the fabrication process as well, and different mechanical deformation to improve the grain connectivity. So these are the some scenario. As you see already, I also in the second or third lecture from Dr. Susie from Oxford, which also found, she also shows some of the crossover things that, you know, when you use the carbon dope, different dope, this crossover is happening. So we can improve the high field, but that also you can decrease the low field. That crossover actually happened if you use the different doping. So the strategy, as published by Sassner, that he proposed some strategy that you see that crossover, we need to improve the infield performance, either by doping or somehow we can improve this by improving the connectivity. So the most important thing, we have to look for homogeneous doping definitely, and we need to look at the quality of the starting materials of MGBT performance. We have to use how to make improve the connectivity of MGBT. These are all important points. Also the flux spinning center to improve the grain. If we can increase the small grain density, it is also improve the grain boundary density, and with the pinning center we can improve also with the impurity scattering. So this is one of our work we actually did quite 2017 actually. So what we improved, the strategies we did, that this carbon doping, carbon encapsulated boron we used, then drawing you see the elongation of the magnesium because of their ductile property, and then we apply the cold high pressure densification, which we first reported in when I was in University of Geneva. So that's CHPD, cold high pressure densification. Actually, before the reaction, we first pressurized in this way. Is a 4-wall pressure. You put the wire here and you apply the pressure from the both sides. So the volume contraction is there. So it just increases the density. So if you look at this, it is just the evidence that the carbon doping is encapsulated. So you see the age, that age actually is the yields actually give us the indication that how that carbon coated onto the boron powder. And these are all lamellar structure in here. And you see the after cold high pressure densification, it even reduced the filament. Okay. So the volume contracted with the filament. So this is the in situ PIT method, and we apply the cold high pressure densification around 1.8 GPa, and also we applied during the reaction, we applied the HIP, which was done in Poland. So these two combinations, actually three combinations, one is carbon encapsulated amorphous boron powder, cold high pressure densification, and HIP, which made us actually very high JC. If you look at around, we actually 14 Tesla, yes, 14 Tesla we measured this wire. You see, this is the HIP 1.4 and this one, and this is the highest so far, the second generation IMD wire, which is very, very close. But IMD wire, you see that it is still, we are concerning about, Hypertech also concerning about the mechanical, poor mechanical properties. So this is actually, there is no IMD, as you know, that magnesium inside, rod inside, which can make a big hole there, but in situ, in this wire, actually that problem is not there. So this is the combination of all these. So you see the voids actually reduced, and we see some nanoscale defects here. So these are the all combination to get that high JC. All right. So now I will just try to explain that this doping actually, as you see, the rolling induced texture is there. So it has some anisotropy. So for magnet design, we have to consider this anisotropy. So we have to have the isotropic wire because it is not the round. So this is where our investigation to check that how the roles of CHPD, carbon doping, all this aspect ratio, effect on critical current density, irreversibility field, and also the N factor and anisotropy. So look at this table. Actually, if this table so we just took the undoped wire, silicon carbide, and malic acid doped wire. So if you look at the tape, we made a tape, so it's rolling induced tape. So if that tape, you see this is the tape cross section. We sintered this temperature 650 for 1 hour, and the filling factor actually, this is the tape, so there is no densification. So this is the filling factor little increase, it's fluctuating, and the aspect ratio, you see the changes. Aspect ratio is the B by A, and this is the anisotropy ratio. And lattice parameter, if you look at the different carbon doping, and the lattice parameter decreased, TC also decreased, which is agreement with the current reported.
You have 3 minutes, Hossain.
Or 3 minutes.
Uh-huh.
Okay. Okay, I'm just going quick. Okay, so the 10 weight percent silicon carbide and malic acid dope, we apply 10%, and you see, and different temperature. In different temperature, you see the anisotropy actually increased with the field. If you look at the different thing, but you see the in malic acid, actually the lower anisotropy than other two, silicon carbide and undoped. So what is the reason? The reason, and okay, so we not only did the JC anisotropy, we also did the anisotropy on N factors, anisotropy of be irreversible. So all these parameters, we check the anisotropy, and we found the malic acid dope is actually the best performed, is very low anisotropy because of there is some reason, or definitely the reason is malic acid is a fresh carbon actually we can get from the malic acid, because we get the malic acid using the chemical solution route. That chemical solution route, from the decomposition of malic acid, we can coat onto the boron. So this is very important, that fresh carbon actually goes there, which is proposed by the dual reaction model by Professor Dow. So this is actually very good evidence of how the fresh carbon actually going into the lattice, and that one actually break that random anisotropy. All right, so another quick investigation we did, because as we know the malic acid is very good, so we applied the CHPD and check the anisotropy as well. So if you look at the tape cross section, and this tape cross section and filling factor decrease, if you check with the different pressure, that the aspect ratio here is important point in malic acid. Even the 2 GPa, the aspect ratio actually higher. But if you go into the real, the JC versus B and the anisotropy, even the aspect ratio is higher, malic acid has lower anisotropy. This is very, very important thing, that how the carbon actually, not only carbon, here the applied pressure of CHPD makes the different defects, and also the nanoscale defects, and also the C-axis grain orientation is also makes the role to get that lower anisotropy. This is if you see the 002 peak is actually, this intensity gets lower. So the C-axis orientation, that subgrain defect, and the fresh carbon goes into the lattice is very, very important, make the role for that lower nearly isotropic wire. All right, so just acknowledgement is my postdoc now working, his PhD student, and Hypertech, Pavesium, NIMS, Polish Academy of Science, and Australian Research Council is all I'd like to acknowledge. And also, definitely, next time, I think you are all welcome to Queensland, in University of Queensland in Brisbane. So, thank you very much.
What was the difference between the two types of carbon on the basically on generating anisotropy? I did not know if you were meaning that there will be some sort of like a mechanical effect, mechanical deformation effect in one case, and something which is not that on the other. Is that, or if it is a different effect from that?
Actually, I missed one point. Sorry, Carmen, I missed one point. There's a 2 carbon. How it was implemented into MGB2, I didn't explain actually, because one was silicon carbide, carbon from from coming from the silicon carbide, another one carbon from the malic acid. So that is, and the processing actually two different. Silicon carbide was applied using the a solid state normal mixing, but the malic acid normal mixing actually, if you look at the, actually I changed the, if you look at the TM, it was totally agglomerated in the solid state mixing. It is not good. But what we make with chemical solution route, actually, it is from the decomposition temperature. When we increase the, the decompose the malic acid, it's just fresh carbon and more carbon actually go into the lattice. So this is the two different processing of doing the carbon doping into the lattice, actually MgB2 lattice. Did I answer you, Herman?